So here we're going to develop something called the unit circle, which is going to be a tool that we're going to use constantly to try to help us do a variety of trigonometric activities. Included in that is converting and memorizing the conversions between degrees and radians for angles associated with 30, 60, 90 and 45, 45, 90 triangles. It's also going to help us to evaluate the sine and cosine and tangent of angles that are coterminal with or have a reference angle of 30 degrees, 45 degrees, or 60 degrees. It's also going to help us define the sine and cosine and tangent of our quadrant angles. So what is the tangent of a 0-degree angle or the sine of a 90-degree angle? Things that are really tricky if we're trying to do it from a triangle perspective, but because of the patterns we're going to develop here, we're going to be able to evaluate all sorts of angles, the trigonometric ratios of all sorts of angles. So the start of this tool is going to be the inner ring that we see here. And so for this inner ring, we're going to use it as our degree measures. And so, of course, starting from the positive x-axis, we have a 0-degree angle. And so then if we rotate a full revolution, we're going to end up at 360. So that's the one spot that's going to have two labels. So if we rotate 180 degrees, that would put us over here. So that's 180 degrees. Up at the top then, this of course is 90 degrees. And so again, all of these rotations are from the positive x-axis over here. So 270 would be at the bottom. So we have our quadrant angles, as we call them. 0, 90, 180, 270, and then 360. And then bisecting each quadrant is going to be the equivalent of 45 degrees. So we know that this here is 45 degrees. And then on either side of it, you can see that it's not right in the middle, so this isn't going to be 22.5 degrees. Instead, this is going to be a 30-degree angle at that location with 60 on the other side. So you can see there's a 15-degree bump in between those, and that's being repeated everywhere else. So if we go to the second quadrant, we rotate over, 30-degree jump gives us 120 at this location. Then we have a couple 15-degree jumps, so 135 and then 150. Moving into the third quadrant, another 30-degree jump gives us 210 at this location, and then 225, and then 240 are the next two. And then finally in the fourth quadrant, we have 300 degrees with that 30-degree jump, and then 315 and 330. And so what all of these angles have in common, all of those that are not the quadrant angles, they all have reference angles that are related to our 30, 60, 90 or 45, 45, 90 triangles. So for example, if we drop a perpendicular right here for this 150-degree angle, well, we can see that this angle right here, the reference angle would be 30 degrees. So the features, the trigonometric ratios of a 150-degree angle, we're going to find are going to overlap with that of a 30-degree angle. The only difference will be in some positive and negative signs. And that's true for all of our angles that we've listed here that are of those not the quadrant angles. So now we can continue with the radian measures. So for the radian measures, we'll use that for the middle ring. And so again, if we have no rotation, we have 0 radians. And so hopefully we remember at this point that a full circle is the 360 degrees, which is 2 pi radians, or the more standard conversion that we've used is pi radians for 180 degrees. So to fill in some more easy spots, half of 180 is 90, so that means half of pi is the radian equivalent, so we're going to have pi over 2 up top here. And then if we continue counting by 1/2, so 0, pi over 2, pi, that means the bottom down here is going to be 3 pi over 2. So we've got those quadrant angles. Next, we can fill in the 45s. So 45, 135, 225, and 315. Those are all our 45-degree equivalents. So 90 divided by 2 is 45 degrees. So pi over 2 divided by 2 is going to give us the radian measure. So pi over 2 divided by 2, or pi over 2 times 1/2, gives us pi over 4. So now every 45 degrees, we're counting a pi over 4. 1 pi over 4, 90 degrees is 2 pi over 4, but it reduces to pi over 2. That means 135 degrees is going to be 3 pi over 4. 180 degrees would be 4 pi over 4, but that reduces to just pi. 225 will be the next 45 degree increment, so that's going to be 5 pi over 4. 270 would be the next, so that would be 6 pi over 4. Again, we're just adding pi over 4 every single time. So 6 pi over 4 reduces to 3 pi over 2. And then if we add pi over 4 one more time, so 6 pi over 4 plus 1 pi over 4, 315 degrees then is the equivalent of 7 pi over 4. And then if we add pi over 4 one more time, we'd end up here at 2 pi. 7 pi over 4 plus 1 pi over 4 would give us 8 pi over 4. Continuing along, we've got, we can go through the 60 degree measures. So remembering that pi is 180, so 60 is 1/3 of 180, so that means the radian equivalent of 60 degrees would be pi over 3. So we've got pi over 3 for 60 degrees. If I add 60, so if I rotate that equivalent distance, 60 plus 60 is 120, so pi over 3 plus pi over 3 is 2 pi over 3. If I add pi over 3 again, so add another 60 degrees, that puts me at 180. So 3 pi over 3 reduces to pi, so that fits as well. Add 60 again, so add another pi over 3, so 240 degrees is going to be 4 pi over 3. And then finally, we've got 300 degrees. If we add 60 again, we end up at 300. So 4 pi over 3 plus pi over 3 gives us 5 pi over 3. If we rotate one more 60 degree interval, we're going to end up back at 0 or at 2 pi. So 5 pi over 3 plus 1 pi over 3 gives us 6 pi over 3, which reduces to 2 pi. And so then the last angles we need to fit in are the 30s. So for the 30 degree angles, if we think about 30 degrees related to 180, 30 is 1/6 of 180. 30 over 180 reduces to 1/6. So that means the radian equivalent of 30 degrees is going to be pi divided by 6, so pi over 6. And so that means every 30 degree interval is 1 pi over 6. So 30 degrees, we have 1 pi over 6. 60 degrees would be next, that would be 2 pi over 6, but that reduces to pi over 3. 90 degrees would be the next 30 degree interval, so that would be 3 pi over 6, so that's pi over 2 if we reduce it. 4 pi over 6 at 120 reduces to 2 pi over 3. And then when we get to 150, that's now going to be 5 pi over 6 at this location here. So 150 degrees is the equivalent of 5 pi over 6. If we keep on going, rotate another 30 degrees, we're back to pi here. So we've got 6 pi over 6, add 30 again, so add another pi over 6. 210 is 7 pi over 6. And then if we skip ahead to 330, if we think of 2 pi as being 12 pi over 6, then if we're 30 degrees short of that, if we're pi over 6 short of that, that means 330 degrees is going to be 11 pi over 6. So if we subtract 12 pi over, or 1 pi over 6 from 12 pi over 6. So here is a tool now that we have that allows us to avoid having to use the conversion factor to find the radian equivalence of any angle between 0 and 360 that has a reference angle associated with our special right triangles. But the real functionality of the unit circle is to help us find the sine and cosine and tangent, and then of course the cosecant, secant, and cotangent of all of these angles. Now, in order to do that, we need the third ring of our unit circle. And so the third ring is the reason we call it the unit circle is because this one is going to have a radius of 1 unit. And so what we're going to do is we're going to figure out what are the coordinates of all of these points that are along this circle that has a radius of 1 that are associated with all of these angles. So to start off with, we can do the easy ones, the quadrant angles. So the coordinate here is, of course, if this is the origin, so then the coordinate to the right 1 unit is just going to be 1, 0. If I go to the top of the unit circle here, if I go up here, again knowing that the radius of this outer circle is 1 unit, so that means the coordinates up there are 0, 1. If I rotate to pi or 180 degrees, now we're -1, 0 is our coordinate. And then down at the bottom, we're of course now down 1 in the y direction, So we've got 0, -1. So those are kind of the easiest ones for us to identify, is these quadrant angle coordinates. So what about these other points that are in between? These are going to be a little bit trickier to find, but we can use our knowledge of 30, 60, 90, and 45, 45, 90 triangles to figure out what those coordinates are. So what I'm going to do here is I'm going to really start to clutter up our diagram, but I'm going to drop a perpendicular and make a triangle here. So this triangle, of course, is a 30, 60, 90 triangle, since I'm drawing the terminal side of this along the 30-degree angle line. So we have a 30, 60, 90 triangle. And I know what the hypotenuse length is because I know that that's the radius of this unit circle. So I know that the hypotenuse here is 1. And if I know one length of a 30, 60, 90 triangle, then I can figure out the rest. So if I know the hypotenuse, I know the short leg, the side across from the 30-degree angle, is going to have a length of 1/2 because I'm going to divide by 2. And then if I take the short leg, I can multiply it by √3 to figure out what the long leg is, the one that's across from the 60-degree angle. So this side here is √3/2. And so since those are the horizontal and vertical movements from the origin here, that means the coordinates of this point are the horizontal movement, √3/2, and then the vertical movement is 1/2. And so we'll see how this is going to be useful to us later. For now, we're just going to generate these coordinates. So now I'm going to jump to the next point right here. So at this location, again, I'm along the terminal side of a 45-degree angle. So I'm going to drop a perpendicular and make myself a 45, 45, 90 triangle. And so again, just like on the blue triangle that we have in front of us, I know what the length of the hypotenuse is. I know that's 1. And then to get from the hypotenuse to the legs of a 45, 45, 90 triangle, I'm going to divide by √2. So we get 1 divided by √2, which of course we can rationalize by multiplying the top and bottom by √2. And so then we end up with √2 over √2 times √2 is 2. So that means both the vertical and horizontal lengths of this triangle are √2/2. And so those are going to be the coordinates of the point that we have here on the circle that has this radius of 1. So we've got √2/2 and √2/2 as both the x and y coordinates. Our last location in the first quadrant is here. So we're going to set up the same thing. We're going to drop a perpendicular to create a right triangle. So again, we're really mucking up our diagram here. Now, we've created another 30, 60, 90 triangle with a hypotenuse of 1. So hopefully we're seeing that there should be some similarity with the blue triangle that we did earlier. It's just we have flipped the 30 and 60-degree angles. So all that means is that we're just going to have to flip the two coordinates because the two side lengths have flipped as well. So instead of the coordinates being √3/2, 1/2, we've got an x coordinate of 1/2 and a y coordinate of √3/2. Now we're not going to have to repeat this exact same thing all the way throughout the entire unit circle, because at this point we've got enough to be able to fill in the rest of the coordinates. If we take this last point that we just made, and if we move over to the second quadrant, the angle that's associated with 2π/3 and 120 degrees, we can see that they have the same y coordinate. I've moved horizontally to that same location, which means I must have the same x coordinate as well. It's just we're moving in the negative direction from the origin. So my coordinates at this point are going to be the same as the other red point in the first quadrant. It's just I'm going to have -1/2 as my x coordinate and positive √3/2 as my y coordinate. And the same thing is going to be true for the other 2 points in the second quadrant. If I draw a horizontal line here to get to this location, we can see I have the same y coordinate, which means I'm going to have the same x coordinate as well, just negative, just like we had with the previous example. So the coordinates here are going to be -√2/2 for x and positive √2/2 for y. And then for the last one, doing the same thing. If I draw that horizontal line over, we can see we've got the same y coordinate, so we'll just have the opposite positive negative sign for the x coordinate. So negative root 3 over 2 and then 1/2. And so we can see that for 30 degrees and 150 degrees, we have the same coordinates here, just changing our positive and negative signs. So angles that are of a measure of 30 degrees or have a reference angle of 30 degrees, like 150 does, we've got the same x and y coordinates, just differing by positive and negative signs. Same thing is true for the 45 degree angles, the 45 and the 135. So 135 would have a reference angle that's 45 degrees. So it also has the same x and y coordinates, just differing by some positive and negative signs. And then at 60 degrees, the pi over 3 and 2 pi over 3 angles, same thing as well. We can go ahead and finish filling out our angles, or our coordinates around the unit circle. So I'll stick with the red. If I drop this line all the way down to here, we can see that we're going to have the same coordinates at this location at 240 degrees at 4 pi over 3 as we had at those other red locations, just both coordinates are going to be negative. So we're going to have negative 1/2 negative root 3 over 2. And then if we slide over to 5 pi over 3, 300 degrees, we can see that's the same y coordinate and the same x coordinate in the as the other red points. So if I draw in these lines here, so we've got positive 1/2 since we're now in the positive direction for x, but negative for y. For the 45 degree equivalents, so the ones that are in purple, so at 5 pi over 4 and at 7 pi over 4, we're going to have all the coordinates be root 2 over 2's. It's just that they're going to be changing their positive and negative sign depending on where we're located. So down here in the third quadrant, we're going to be negative root 2 over 2 for x and negative root 2 over 2 for y. And then for the one at 315 degrees at 7 pi over 4, we're going to have positive root 2 over 2 for x, but negative root 2 over 2 for y. And then lastly, we've got those 30 degree equivalents, the angles that have 30 degrees as their reference angles. So those are all of the ones that are in blue. So again, if I drop my line down here, I can see that I've got the same x and y coordinates, just both negative here. So negative root 3 over 2 and negative 1/2 for x. And then finally, the last point here in the fourth quadrant, we can see that we're going to be back to positive for x, so root 3 over 2, but then negative 1/2 for y. So I've uncluttered our diagram a little bit so that we can now see what is the point of all of this. How are these coordinates going to be useful for us when it comes to finding the trigonometric ratios of all of these angles? So let's take this location right here. So if I again create a right triangle here, so I have this 30, 60, 90 triangle. I know this angle here is 30 degrees. I know that the one up top is 60 degrees. So if I wanted to know what is the sine of this 30 degree angle, what is the sine of pi over 6? Well, we can say that it's the opposite over the hypotenuse. And again, we know that the hypotenuse is 1. So if I'm going opposite over hypotenuse, what I really just need to know is what is that opposite side. And that opposite side is, of course, 1/2, since it's going to be half of the hypotenuse, which is the y coordinate right here. So the sine of 30 degrees, in this case, is 1/2. If I do the same thing and jump up to 45 degrees, I drop a perpendicular there, create a right triangle. Again, my hypotenuse is 1. Now I have a 45, 45, 90 triangle. Well, to find the sine, I'm going to go opposite over hypotenuse. Well, what is this opposite side right here? Well, it's root 2 over 2, which is, again, the y coordinate. Sine of pi over 4, or sine of 45 degrees, is root 2 over 2, the y coordinate associated with that point. If we draw another right triangle for the point here in red, so again, hypotenuse is 1. If I want to find the sine, it's going to be sine of 60 degrees. We can write it in degrees this time. It's going to be that opposite over hypotenuse, which again is root 3 over 2, which is the y coordinate. Or in other words, the sine of any angle, so the sine of some angle A on the unit circle is just going to be the y coordinate of that angle anywhere on the unit circle. Because if I rotate to one of these angles over here, so let's say I'm at 120 degrees. So there's my terminal side. Well, to find the sine, cosine, and tangent, I'm going to need a reference angle. So I drop my perpendicular. So this is the reference angle that we're going to use. Well, to find the sine, I'm still going to do opposite over hypotenuse. Well, my opposite side here is going to be the same. It's going to be the y coordinate. It's going to be √3/2. And so that pattern holds everywhere around the unit circle. So I'm always able to find the sine of an angle by just identifying the y coordinate associated with that angle on the unit circle. For cosine, same thing, except now we need the adjacent side. Well, what's the length of the adjacent side with any of these angles? Well, it's going to be the x coordinate. So cosine of some angle A on the unit circle, we know what its cosine is without having to touch a calculator by just knowing what the x coordinate is. So I've uncluttered our diagram a little bit so that we can now see what is the point of all of this. How are these coordinates going to be useful for us when it comes to finding the trigonometric ratios of all of these angles? So let's take this location right here. So if I again create a right triangle here, so I have this 30, 60, 90 triangle. I know this angle here is 30 degrees. I know that the one up top is 60 degrees. So if I wanted to know what is the sine of this 30-degree angle, what is the sine of pi over 6? Well, we can say that it's the opposite over the hypotenuse. And again, we know that the hypotenuse is 1. So if I'm going opposite over hypotenuse, what I really just need to know is what is that opposite side. And that opposite side is, of course, 1/2, since it's going to be half of the hypotenuse, which is the y coordinate right here. So the sine of 30 degrees, in this case, is 1/2. If I do the same thing and jump up to 45 degrees, I drop a perpendicular there, create a right triangle. Again, my hypotenuse is 1. Now I have a 45, 45, 90 triangle. Well, to find the sine, I'm going to go opposite over hypotenuse. Well, what is this opposite side right here? Well, it's √2/2, which is, again, the y coordinate. Sine of pi over 4, or sine of 45 degrees, is √2/2, the y coordinate associated with that point. If we draw another right triangle for the point here in red, so again, hypotenuse is 1. If I want to find the sine, it's going to be sine of 60 degrees. We can write it in degrees this time. It's going to be that opposite over hypotenuse, which again is √3/2, which is the y coordinate. Or in other words, the sine of any angle, so the sine of some angle A on the unit circle is just going to be the y coordinate of that angle anywhere on the unit circle. Because if I rotate to one of these angles over here, so let's say I'm at 120 degrees. So there's my terminal side. Well, to find the sine, cosine, and tangent, I'm going to need a reference angle. So I drop my perpendicular. So this is the reference angle that we're going to use. Well, to find the sine, I'm still going to do opposite over hypotenuse. Well, my opposite side here is going to be the same. It's going to be the y coordinate. It's going to be √3/2. And so that pattern holds everywhere around the unit circle. So I'm always able to find the sine of an angle by just identifying the y coordinate associated with that angle on the unit circle. For cosine, same thing, except now we need the adjacent side. Well, what's the length of the adjacent side with any of these angles? Well, it's going to be the x coordinate. So cosine of some angle A on the unit circle, we know what its cosine is without having to touch a calculator by just knowing what the x coordinate is. And the tangent of an angle A is going to be the opposite over adjacent, or the y-coordinate over the x-coordinate. And so beyond just finding the sine, cosine, and tangent of any angle that has 30, 45, or 60 as a reference angle, we can also use the unit circle and extend the pattern described here, where sine is the y-coordinate, cosine is the x-coordinate, and tangent is y over x, to finding the sine, cosine, and tangent of our quadrant angles. So for 0 degrees, or 90 degrees, or pi radians, etc. Because those angles, we're not going to be able to draw a right triangle, but we can find what the sine, cosine, and tangent ratios are by just looking at the coordinate, extending this pattern. So for example, the sine of 0. Sine of 0, I look at the coordinate, that's 1 comma 0. Sine is the y-coordinate, so that means the sine of 0 is 0. Or if I take the cosine of pi, let's say. So I go to pi radians, my coordinate is -1, 0, and so therefore I take the x-coordinate, cosine is the x-coordinate, so I know that the cosine of pi, the cosine of 180 degrees, is -1. So now the sine, cosine, and tangent ratios of these quadrant angles become possible as well using this unit circle as a tool.